focus on the second, also because the models that you use to perform ecological risk assessment are different. And I must say that ecological risk assessment is a topic of applied research nowadays. It's complex, okay, while health risk assessment is comparatively simpler. It is not simple in itself, but it is simpler than ecological risk assessment. So risk assessment, when we speak about health risk assessment, now risk assessment for short, we mostly focus on contaminants. And it is, as I was saying, a tool to support decisions. So a tool to inform decision. It is not the only tool, of course, as all decision support tools that we have seen in this course, they must be applied often together in a portfolio-like type of action. It is usually, this assessment is usually carried out to estimate the risk given by an hazard. In a moment, we'll see what an hazard is, in order to choose between different management options and or to define how much a site is contaminated, and so what are the goals for its remediation, bonifica in Italian. There are so many definitions of risk. And risk assessment. For example, in the Italian regulation, which is Testo Unico from 2006, there's a section dedicated to the remediation of contaminated sites. This piece of policy has been updated, but it is the main reference when dealing with risk assessment. And you find in that Testo Unico you can find about site-specific environmental and health risk assessment, which is a site-specific analysis of the effects on human health due to prolonged exposure to the action of the substances found in contaminated environmental media, for example. So if you look at the handbook of APAT that you see, it is in Italian, of course, but there's a translation here. Risk assessment is rather defined as a systematic process, so a well-defined process for estimating all significant risk factors involved in an exposure scenario caused by the presence of an hazard. So when you think about risk, this is a very simple definition, but you should remember it because it's very effective. You should break down risk into two components that are multiplied one by another. So risk is the product of P and D. You can think of it as the product of P and D. P is the probability that an hazardous event, so an event that causes harm to humans, takes place. So the probability of, I don't know, spillover of a contaminant by a factory into groundwater. And D is the magnitude of the harm caused by the hazard, so the spillover in this example. Of course, the spillover of a very toxic contaminant will have a different D compared to the spillover of a slightly toxic contaminant. So even if the probability is the same, the risk in the case of very toxic and slightly toxic contaminants is different. And you can think D, the magnitude of the hazard impact, as the product of a danger factor, toxicity, okay, and a factor which express how much humans, in the case of health risk assessment, come into contact with the contaminant in the case of toxicity. And this is called exposure. Of course, if a contaminant is spilled in groundwater, but nobody drinks that groundwater, the exposure term is very low. If a lot of people drink that groundwater, exposure is high, and so the risk is different. This is a very simple definition, but you should remember it because it contains everything. The fact that risks, it's not something certain, it's something that happens with hazardous events taking place with a certain probability, and this definition is sort of objective because these are things that you can measure. Of course, when you're dealing with contaminated sites as environmental engineers, the probability of contamination taking place is by definition equal to 1 because the site is already contaminated. So risk is simply the product of toxicity and exposure in the case of already contaminated sites. Let's make a very simple example. For example, I took this data from the Italian Statistics Institute. In Italy, in 2007, there were about 230,000 car accidents per year in that year. And in Italy at that time, there were about 59 million inhabitants. And there was one dead person every 45 accidents and 1.4 injured person per accident. So if we want to calculate the risk of death due to a car accident, we must multiply what we call probability by the magnitude of the car accident hazardous event. So the risk of death due to a car accident is the number of car accidents divided by the number of inhabitants. This bit here is the probability of you being involved in a car accident. This is a rough calculation, of course, because of course not everybody uses car, but this is just for the sake of simplicity. And this is the magnitude 1/45. So the risk is 9 dead every 100,000 inhabitants per year. You can also do the same calculation for the risk of being injured in a car, and you get that there's 1 injured person every 180 inhabitants per year. And this is the risk of being injured in a car accident using the very simplified calculations of probability that I have just shown. By the way, it's a very high risk if you think about it. Yeah, I hope this should make things clear. So, sorry, your colleagues keep coming, I'm letting them in. And okay, so as I was saying, risk assessment is a decision support tool in environmental engineering. You can use it, these are just definitions, in retrospective mode, that is to evaluate the possible harm due to a contamination that's already taken place in the past. Or you could use it in a predictive mode, so to predict the possible future harm caused by something that you're going to do, such as constructing a landfill. More important is the difference between direct and inverse risk assessment. With direct risk assessment, which is sort of more intuitive type of assessment, you evaluate, the contamination, and then you calculate the risk, okay, just very linear, on-site or off-site. While the inverse or backward mode is usually done in the case of remediations. So you define an acceptable risk in the in your area of investigation. And based on that acceptable risk, you back calculate the concentration of contaminant that gives that acceptable risk. So that concentration is the goal for your remediation action. Very simple. Also sorry, I see some comments in the chat. Yes. If you don't hear, please tell me. There you can classify risk in point and diffuse. The distinction is quite straightforward. By point risk, we mean the assessment of a risk in a certain location, in a specific geographical point. And while and this point risk can be estimated as local risk or individual risk. When you speak of local risk, you usually speak of a hypothetical target. This will become clearer later, such as a person that's always found in that given location without the possibility of moving or protecting. While individual risk takes into account the specificities of individuals, such as, I don't know, let's make an example. Think about air quality in Padova. You know that the Po River floodplain, the Padana plain, is one of the most polluted areas in Europe because of its particular weather condition, and also because of the high density of human activities in it. You could think of a person commuting, I don't know, from the mountains to Padua every day, and assess the health risk assessment in the case of that person commuting from in and out of the Po River floodplain. So he is exposed to bad air quality only during a fraction of the day because this person commutes. So we're speaking about individual risk. Local risk, instead, is the risk in the case of air quality that you experience in the case of people staying all the time in the Po River floodplain. And you could visualize risk, for example, in reports through ISO curves or risk profiles. Plots are very clear in regards to this. The one on the right is the risk profile. So on the abscissa, you have the distance from the, for example, from the contamination, this one here. And this is the risk. So the risk decreases as you go away, as you see, as you go away from the contamination, for example. This is a risk profile. So this is a one-dimensional representation, while this on the left is ISO curves. So every one of these lines that I'm indicating with the arrow are represent location with the same level of risk. Okay, so for example, risk here is 10 to the minus 6. I don't know the unit of this example per year, and so on. And you see that in this other case, the risk is lower. So you can guess that in the center of the circle here, the risk is maximum because it's where the place where the contamination took place. And of course, it all boils down to how you can calculate these profiles or these ISO curves. And you need to, of course, use models. And we'll get to this during this lecture. So let's go. Is there any question? You remember, I also told you that you can have diffuse risk, which is not in a precise location, but it's rather a general, a global measure of the risk to which a community of people is subject in a given area. So, for example, in a city, or in the Po River floodplain, for example. So a broad geographic area. The meaning of the term broad, of course, depends on the context. So you usually need demographic data to estimate these diffuse risks, such as the age distribution of the human population, and in particular, the presence of sensitive targets. For example, people who are already ill or old, children, why children? Because they weigh less than adults, so they can bioaccumulate less contaminants. They can dilute them in a lower body weight, so they can be sensitive targets. Because of this reason, presence of fluctuations of human population, for example, due to commuting, as I was saying. And yeah. And again, you have methods for estimating this and visualizing this kind of risk, such as FN curves and IN histograms. And this is just an example of an FN histogram. You have here, sorry, I'm trying to visualize the pen tool of Zoom. Okay. So here you can have the frequency of the predictive frequency of the hazardous event. And here you have, for example, the number of victims per event, and this is an FN diagram. Just example, this is not really the topic of the lecture. Okay, so there are some novel concepts I would like to highlight that are important to realize for you when you deal with risk assessment. The first thing is that risk contains a probability term. So risk is something that is not certain. This is important to remember, that you deal with probability and not with deterministic models. And the second thing that's very relevant nowadays in the times of pandemic is that when you are engineers, so you like to, your job will be to deal with objective ways of quantifying information to support decisions. Unfortunately, in risk assessment, perception, human perception comes heavily into play. And this is very important because engineering, environmental engineering is not only about making calculations, but also about communicating decisions, communicating results. And so you should be aware of the fact that most people, everyone actually, have a distorted perception of risk. In particular, think about the fact that we live in a very polluted floodplain, the Padana Plain, the Po River floodplain, but people have a distorted perception of this risk because it's related to a condition that's basically always present, so very frequent, which is bad air quality. So in the case of very frequent events, people tend to underestimate the real risk compared to what calculations in risk assessment show. While instead, in the case of very rare events, such as, I don't know, an incident to a nuclear power central, okay, people tend to, in the case of very rare events such as the nuclear accident, people tend to overestimate the risk compared to what models show, because nobody actually wants to live close to a nuclear power plant, it was the word, although the probability of an accident are very, very low, the risk is also very, very low. So people, every one of us, cannot weight a risk as objectively as models, and this has to be taken into account when communicating it. And also another concept to remember is the fact that zero risk is impossible, okay? Meaning that it may be technically impossible to achieve, or also economically unfeasible to achieve. I remember when I was a student, my professor teaching me air quality modeling and and technologies to clean emissions from factories. He told us that you should never trust somebody speaking about zero risk, because zero risk is technically impossible. And this is tricky to communicate, of course. And risk assessment, as I was saying, is a decision support tool, which is, of course, relevant for environmental impact assessment. So risk assessment can be part of an environmental impact study, but these are, of course, different things. And regarding the regulation, the Italian regulation, very quickly, because some of you are not Italian, in 2006, we moved away from previous legislation, which was from 1999, and basically was based on a straightforward relationship between concentrations of contaminants and the decisions to be made. So if you had a certain value of concentration in a contaminated media, if that value was above a threshold, then you had to do remediation. At present, this approach has changed, and the decisions to remediate or not a contaminated site are made based on a site-specific risk assessment. So no more a tabular approach, just simple tables, but site-specific modeling, quantitative modeling. So this is just the structure of that legislation, but we don't need to go through them. This is what's important. In the Italian legislation, you find this CSC, contamination threshold concentration. So these are the contamination levels of environmental media, and by media I mean water, soil, and so on, above which you should characterize the site and make a site-specific risk assessment. So if your concentration measuring the environmental medium, so for example, the soil you're dealing with, if your concentration is lower than CSC, according to Italian legislation, the site is not contaminated. If the concentration is higher than CSC, you carry out a risk assessment for that site. So you do modeling, as we'll see in the next slide, and using site-specific measurements and parameters, and you determine this CSR, the risk threshold concentration. So the contamination level of your environmental media or medium, which is site specific, whose exceedance leads to a significant risk for health. So if your concentration measured in environmental media exceeds this CSR that you have calculated with models, then your site should be secure and remediated. If, however, concentrations are below CSR, the site is not contaminated. So basically, when you are above CSC, you do a risk assessment and you calculate acceptable concentration, which are different from zero risk concentration, as I was saying. These acceptable concentration are CSR, and if your observed concentration C is higher than CSR, the site is contaminated and should be remediated. So a potentially contaminated site, by definition, you can guess it, is a site where you have concentrations of contaminants higher than CSC, but where risk assessment still has to be done to determine, to calculate CSR. Okay, so a contaminated site by definition is a site where CSR values are exceeded, and a contaminated site is a site where contamination is lower than CSC, or if higher, lower than CSR, which is site-specific threshold. By remediation in Italian legislation, we mean any action aimed at eliminating the sources of pollution and the pollutants, of course, or aimed at reducing the concentration of pollutants below the CSR level. This is important. Okay, so remember, there is no zero risk. Okay, according to Italian legislation, it is okay to leave residual contaminants in a contaminated site if those residual contaminants after remediation do not pose a risk. So if the concentrations are below CSR. And we also have a definition for emergency securing, which is any short-term measure that you have to implement in the case of contamination to limit the spreading of the contamination while waiting for possible remediation actions, risk assessments, operational and permanent security. These are just definitions. This is just a flow diagram of what I have already told. So this is just for your records to look at home. So you guys, what's important here is to define is how you can calculate CSR. So which is basically, if you think about the definition I told in the beginning, an inverse risk assessment procedure. So you define the acceptable risk, you calculate CSR, and then you, based on that CSR, you understand if your concentration is above or below that threshold, and so if you need or not to do remediation. There are technical annexes to Italian legislation telling you how to do this. And in particular, the choice of, tell you how to do this also in terms of modeling and approaches. For example, the choice of modeling parameters when you perform a risk assessment. We'll see some examples in the next slides. The parameters must be chosen conservatively and site-specific. Site-specific, of course, is clear. For example, when you are dealing with the groundwater contamination, you want to assess the, I don't know, the conductivity, hydraulic conductivity of the soil that's contaminated. You cannot use parameters parameter values for sand if your site is gravel. But it's important that you must be conservative. For example, if you are not very sure about the value of the hydraulic conductivity in your groundwater, maybe you have a range of possible parameters. You should choose the worst. Okay, so you should be conservative, precautionary is the right word. You should be precautionary. So choose the worst scenario when doing calculations. This is very important. So you're sure, so that you're sure you are not underestimating risk. And so what you need to characterize are, of course, contaminants, are the sources of contamination. We'll see all of this, the pathways through which the contaminants reach the targets, and the modes of exposure and the targets. So, for example, the types of people, so the age, the weight, and so on, that may be affected by the contaminants. And of course, the calculation of risk must be made following sound scientific methodologies. So what is a sound scientific methodology? Results, for example, should be reproducible. So you should explain the methodology that you have used, the values of the parameters that you have used, the assumption that you have made, and references for the models that you have used, and so on, just like in a scientific paper. So as this slide aims to show, it's risk assessment, site-specific risk assessment is based on the quantification of contaminant properties, the upper edge of the pyramid, of the migration pathways and the modes of exposure, so the way that contaminants come into contact with targets, and also with final receptors, so the targets. And there are technical guidelines that you can have a look at, which you can find online. And so just to break it down in a very simple way, when you assess risk, when you evaluate risk, you basically have two steps. The first is to determine the risk, I will see in a moment. And the second step is to compare it with the level of acceptability found in legislation. I've shown the example of Italian legislation before. And so the steps which you should follow in risk assessment are very similar to the ones that you follow when constructing an ecological model. I know that some of you should be following the class of Luca Palmeri, modeling and control of environmental systems. So the first steps is, of course, the formulation of the problem. So the question which you want to ask, and in particular, you should draw a conceptual model of the site. So how the contaminants move, where they are found, where are their targets, and so on. We'll see an example. Then you should characterize all the pieces making up risk assessment that I have talked about before. So the source, the pathways and modes of exposure, the target, and then you can calculate the exposure. Remember the definition of risk, and then you, based on exposure and toxicity, you can quantify risk. So what's a conceptual model of the site? It can be a drawing, a scheme like this one here, where that's useful to identify the characteristics of the contaminated site and the relationships between them. So you should identify the source of contamination, the pathways of contamination, and the target that you care about in your risk assessment. This is a very simple example. You have a source. This is your source of contamination, a spill over of a contaminant. that gets to groundwater and it floats above groundwater because of its chemical properties and its physical properties. So this is the source, this spillover, and then the diffusion of that contaminants in the groundwater. This is a diffusion process. This is a pathway. And then you have a well where people, if I can make it, where people like this guy drink, and this guy is the target. Okay, this guy is what you care about in your risk assessment. So this is an example of a conceptual model representing sorry, all you need to know. I'm trying to delete my own drawings. Here I am. So, of course, that's a simple conceptual model of a risk assessment. Things in practice are usually much more complicated. You can have multiple sources, you can have multiple pathways, transport processes, you can have multiple modes of exposure, you can have multiple targets. Okay, things can be complicated. Again, regarding definition, when you speak about source, you can have a primary source of contamination. So the chemical element, the substance that's causing pollution, such as spilling of sewage into a river, or you can have secondary source of contamination of risk, which is the contaminated environmental sphere, so the soil, the water, the air. These are just definition. Examples of how you may want to characterize a source. For example, in this example here that I was making before, characterizing the source may mean understanding how big the polluted area of the polluted volume of soil is. And just to remind you of the fact that you need to be precautionary. If in doubt, you should assume that always assume the worst case scenario. Okay, so that a lot of soil is contaminated if you don't know it. For example, typical parameters you may want to quantify in the case of saturated groundwater zone to characterize the source are the Darcy velocity, the hydraulic conductivity of the soil, the hydraulic gradient, the porosity, the dispersivity, the degradation of the contaminant, the degradation coefficient of the contaminant you're dealing with, which may be difficult to quantify. Again, this is an example. So you may decide to neglect it because that's precautionary. If you neglect, if you are not sure about the degradation rate of your contaminant, you neglect it because that's precautionary. And the source must be characterized not only physically, but also with regards to the released contaminants. So in the all the things you already seen in the other classes of Lucas. So you should characterize the physical properties and chemical properties of the contaminant, such as the concentration, the density, the Henry constant, the KOV coefficient, and its toxicological properties. And its toxicological properties can be bioconcentration factors, biomagnification factors, toxicity measures. I'm going quickly because these are things you should already have seen in the classes of Luca and possibly also in the classes of Alberto Privato. So bioconcentration factor is simply the ratio between the concentration of a contaminant in the body of your target divided by the concentration in the environment under equilibrium conditions. And you, in the case of particular contaminants such as those that tend to attach to lipids, you can calculate that BCF factor based on the fraction of lipid in the body and the KOV of the contaminant. And when we speak of biomagnification, this is more difficult to quantify, actually. It's a matter of research. We mean the fact that pollutants are usually found in higher concentration in the flesh of organisms which are predators, because, for example, this is more easy to see in the case of fishes. Why that? Because the big fish is the small fish, and it's a lot of small fishes throughout its lifetime, so it absorbs a lot of contaminants, and it excretes not so many of those contaminants because big animals have slow metabolism. For this reason, you usually find a lot of pollutants after in big fishes. And that's one reason why it is much healthier to eat small fishes such as sardine or anchovy rather than eating big fishes which can accumulate, for example, heavy metals such as tuna. When you're dealing with toxicity, parameters you can find in databases or books to represent toxicity are no effect concentration. We'll see the definition in a moment, or LD 50, for example, the lethal dose which kills 50% of test organisms such as, I don't know, Daphnia. And LC 50 is the lethal concentration, not dose, but concentration. So different unit of measurement which kills 50% of organisms in an experiment in the lab, or you can have effect concentration 50, concentration showing a given effect, I don't know, reduction in growth in 50% of organisms. And these are about short-term toxicity, while in the case of long-term toxicity, you can use the hazard quotient. It is a ratio which expresses how many times the exposure to a substance, to your contaminant, is higher than the acceptable dose. So the definition is the one you see below in this slide. So hazard quotient is equal to exposure. So how much contaminants you are exposed, your target is exposed to, divided by a reference dose. Reference dose is the daily average exposure to a contaminant which does not yield negative effects on humans during their whole lifetime. And you see the unit of measurement is milligram of contaminant divided by kilo of body weight per day. So of course the reference dose is also linked to the weight of the person, so to your target, so to the characterization of your target. Those toxicity indicators that I've listed, they are fit for non-carcinogenic substances, while substances which can give you cancer, so carcinogenic, are different because there is no threshold, okay? There is no RF, the reference dose, below which the absorption, the uptake, sorry, of a certain contaminant dose is safe. Even a very small uptake of a carcinogenic substance can give cancer, because that's how carcinogenic substances work. There is no threshold effect. So when to quantify toxicity of carcinogenic substances, you speak about incremental probability of cancer. So R here is the incremental probability of cancer during lifetime caused by the exposure to the carcinogenic substance. Incremental means below the background level of cancer due to other causes in the population. And then that incremental probability is the product of exposure by a slope factor, SF. So any non-zero exposure will generate an incremental probability of cancer. If you think about this definition, there is no threshold. This is shown in this plot here. This is the response. So for example, the incremental probability of cancer or the toxicity, the negative effects, sorry, that you can have, for example, cancer on your population. And this is the dose of contaminant you come in, your target population come into contact with on the abscissa. And you see that carcinogenic substances, sorry, here I am. And you see that carcinogenic substances, any dose of carcinogenic substances yields a response, while a non-carcinogenic substance yields a non-zero response only after a certain threshold. And RFD, which is the safe dose, is of course lower than that threshold. I think this plot is what you need to remember. It's, in my opinion, it's clear enough. Okay, so then you need to characterize the transport of the contaminant, so the pathways through which it goes from the source to the target. And of course, those pathways can be one or many, depending on the case you're investigating, because different, and also on the contaminant, of course, because contaminants can move through air, water, soil, and whatever. So of course, I cannot make general statements. You should use transport models to characterize the transport of the contaminants you're dealing with. For example, in the case of air quality, there are many models available for free, developed, for example, by environmental protection agencies in the world. Same for surface water, contamination, groundwater, and so on. Again, remember that sometimes for the sake of simplicity, because several of these models are very complex to set up and require a lot of data, which you usually don't have, what you do to calculate transport is simply to multiply your concentration at the source by a transport or natural attenuation factor. So you have your concentration at the source here. You calculate your transport factor, which will be lower than 1, of course. And then your concentration of contaminant in the point of exposure where the target is simply that transport factor times the source concentration. So the transport factor may take into account, for example, processes such as dilution, leaching into groundwater, volatilization, dispersion, hydraulic dispersion, air dispersion, and things like that. And there are, of course, models, equations you find in technical guidelines to estimate that transport factor. Those equations, those simple models are usually based upon assumptions, simplifying assumptions, such as, or precautionary assumptions, such as pollution concentration, which is uniformly distributed and constant in the exposure period, homogeneous isotropic soil, and no biodegradation rate if you want to be conservative. And this is just an example to calculate the leaching factor, which takes into account the fact that concentration of a contaminant in soil and groundwater is attenuated during the transport from the source to the groundwater due to infiltration into the unsaturated layer and dilution. So you can have simple, as I was showing, or very complex manners to calculate that leaching factor based on parameters such as the density of the soil, the Darcy velocity, the width of groundwater, the distance, and so on. Yeah, these are very specific models and size-specific models. And then you have to characterize exposure, which is the way by which organisms come in, humans, in the case of health risk assessment, come into contact with the contaminant. And so when you quantify exposure, you actually need to characterize your receptor in terms of, I don't know, weight, but also in terms of behavior. For example, think of the contamination of a soil in a park where people go sometimes to play, for example. So people come into contact with the contaminated soil only when they are there and only when they play. And if they play in winter, they come into contact with the contaminated soil in a different way than in summer, because in summer there's more exposed skin that can come into contact with the contaminated soil. Or in the case of contaminated water that people use for drinking, the exposure depends on how much water people drink and on how much water they buy at the supermarket, for example. So non-contaminated water, on how much often they drink. So on the frequency of the exposure and on the behavior. Again, these things may be difficult to quantify. So you may want to make simplifying precautionary assumptions to quantify these parameters that I'm talking about. For example, exposure, actually, you calculate it as the product of the concentration of your contaminant in the point of exposure that you have previously determined by quantifying the transport factor, times the actual extent of exposure, so the daily quantity of ingested water, soil, inhaled air per unit of body weight. Again, a scale on the weight of your target. And again, there are simple equations to calculate this EM, so which are a function of the quantity of medium which you come into contact with per unit time, the frequency of exposure, the duration, the body weight, and the average exposure time. Of course, if you remember, I go back a bit. It was you see there's lifetime here. Okay, there's the word lifetime. And also here, all life. So when you deal with toxicity, you must make calculations over the lifetime of your target, because some pollutants can bioaccumulate, can accumulate into the tissues of human body. So you also need to assume average exposure time, for example, 70 years for carcinogenic substances, because this affects the final risk calculation. These are just example of EM factor calculations. For example, in the case of dermal skin contact with contaminated soil, one parameter may be the surface of skin exposed, so that can come into contact with the soil. And yeah, these are just examples that you can have a look at home. I'm going quickly because I'm late, sorry. For example, in the case of surface water which is polluted and people are taking baths in that water, one parameter may be the frequency, the number of days per year that people swim in that water. Okay, one parameter that may come into play in that EM characterization. Of course, there are tables that suggest possible parameter values, but you need to remember the risk assessment is site specific, so you should try to adapt those parameters to your specific site of investigation. And when in doubt, you should be conservative in your assumptions so that you're sure that you don't underestimate risk. And so usually it happens, sometimes it happens that when you have a single contaminant, you can have more than one pathway through which that contaminant gets to your target. So what you do is to calculate the risk for each pathway or the hazard quotient for each pathway and then sum them. Sometimes you have more than one contaminant which can reach your target through one or more exposure pathways. And so what you do is to sum risk or HQ over pathways and over substances. There's a very important assumption in this approach of summing risks coming from different contaminants or different pathways. The very important assumption is that risk is additive. While in many cases, we don't know for sure if risk is additive or rather if there are synergies between different contaminants. This is very important, okay, to remember. It's a matter of research, but it is an assumption you usually make. I remember this is very relevant, for example, in the case of pesticides. In the case of pesticides, usually pesticides contain mixtures of different chemical compounds, and each chemical compound can generate a risk. And you don't know how, because we don't have enough knowledge, you usually don't know how these different compounds interact, acting on human metabolism and physiology. So the last thing we need to mention is that in risk assessment, we also characterize targets, of course. Here we're speaking about humans, since we're speaking about health risk assessment. And so you need to decide whether you focus on resident or commuting people, on workers, or on general laymen that found in a certain place. If you focus on visitors for recreation, if you focus on children, if you focus on sensitive targets, people that have other health problems, and you should also characterize the modes of exposure that can be direct and indirect, as I was mentioning in the beginning. And some quick definition. you have the point of exposure, so the point where the exposure is evaluated, and you have the point of conformity in the case of groundwater, which is the point where the concentration of the contaminants found into groundwater must be lower than CSR. And sorry, so this is it. So just a slide, couple of slides, yes, 2 slides to summarize. So we've seen the risk is the product of the probability of an hazardous event taking place and the magnitude of that hazardous effect. If you have a contaminated site, probability is equal to 1. And then the magnitude can be expressed as done here as the product of your pollutant toxicity and your exposure, your intake of contaminant. The exposure in the points of exposure you can calculate as the concentration of your contaminant in the point of exposure time the actual extent of exposure, which you can calculate with simple models and precautionary assumptions. And the concentration in the point of exposure is the concentration in the source of contamination times a transport factor, which quantifies how concentration of contaminant changes when transported through air, soil, water. So you see that risk is actually the product of many different terms. Any of these terms contains a model, a submodel, so equations that can be simple, they can be complex, they require many parameters which need to be as much size specific as possible. And when in doubt, you should choose precautionary values for those parameters and and choose precautionary submodels and make precautionary assumptions. One last slide about risk tolerability. Remember, I told you that speaking of zero risk actually don't make sense. It's sometimes impossible, technologically impossible or economically unsustainable to get to zero risk. So what is, according to guidelines, a tolerable risk? In the case of non-carcinogenic substances, this is easy. So the hazard quotient must be lower than 1. In the case of carcinogenic substances, this is more tricky because even tiny amount of a carcinogenic substance will generate an incremental probability of cancer. So usually in the literature, you find that values such as 1/1 million are tolerable for carcinogenic risk due to a single chemical, or when you have many different chemicals, carcinogenic chemicals, 1/100,000 is a tolerable threshold. And of course, these numbers these numbers depend on what we as a society think that a sustainable risk is, and that may vary depending on societal values, of course, on culture, morals, politics, and so on. And yes, I'm done. I'm sorry for taking it a bit longer than expected. Please, if you have any questions, you're welcome to ask.